Hello, this is Mrs. Taylor, and I'm going to talk to you about evaluating limits involving infinity. More specifically, limits as x approaches positive or negative infinity. And even more specifically, we want to focus in on the finite limits as x approaches positive or negative infinity. And what that means is as your graph is moving infinitely to the right or infinitely to the left, it's actually approaching a specific y value instead of positive or negative infinity as well. So what that looks like notation-wise, you have limit as x approaches infinity of f of x, or the limit as x approaches negative infinity of f of x. And what we're really asking when we write that out is, as x approaches positive infinity, what is that function doing as it moves to the right? And as x approaches negative infinity, will be what is it doing as it moves to the left? So this is different than sided limits, because with sided limits, we're asking what y value is it approaching from the right or from the left. So we're kind of zeroing in on a specific x value with sided limits. But with infinite limits, as x approaches infinity or negative infinity, we're asking to the right and to the left. So as you move far out to the left or right of the function, what is it approaching? So let's look at this function, f of x equals 1 over x. And let's say I wanted to find the limits as x approaches infinity and negative infinity. When we first approach this scenario, we kind of want to think about the behavior of the graph. And I don't actually have to know what it looks like to know something about its behavior. So think about, if you could, think about infinity as an actual number. So instead of a concept, think of it as actual value. Infinity is a really, really, really big number if you try to think of it as a number. And so if I have 1 over a really large number, let's say we were evaluating this limit using substitution, and I plugged infinity in for x. That's 1 over a huge number. And then as we continue further to the right, that number is just getting bigger and bigger and bigger. And 1 over a really big number is practically 0. You're going to have like 0.000000000 something if you converted it to a decimal. And so as I move infinitely to the right, this function 1 over x will get closer and closer to 0. So the limit of 1 over x as x approaches infinity will just be 0. And then negative infinity would be out to the left. And if I am plugging in a bigger and bigger and bigger negative number, and I guess technically since they're negative, really you're kind of making it smaller, but the numeric portion itself, without the negative, it's just getting bigger and bigger and bigger. And so still you're approaching 0. Even though it's negative infinity, moving out to the left, it's still coming down to 1 over a really huge number. Even if it's negative 0.0000004, that's really close to 0. So basically this limit would equal 0. And if I look at this function, 1 over x graphically, I arrive at the same conclusion. Infinitely to the left, as x approaches negative infinity, it's getting closer and closer and closer to the x-axis. That's y equals 0. Infinitely out to the right, as x approaches positive infinity, it's getting closer and closer to the x-axis, which is y equals 0. So graphically, I can support what I arrived at theoretically, just thinking through the behavior of the graph. Now, you actually kind of know about these limits because you know about horizontal asymptotes. Now, you may not have been taught horizontal asymptotes as limits, but the formal definition of a horizontal asymptote is the limit as x approaches infinity of f of x equals some number, or the limit as x approaches negative infinity of f of x equals some number. And so that number is your horizontal asymptote. It'd be y equals whatever that number is. And so anytime I ask you to find a horizontal asymptote, actually asking you to find a limit as x approaches positive or negative infinity. And so if I asked you to find the horizontal asymptotes of f of x, which is 2 plus 1 over x, I'm really asking you to evaluate each of those limits. And so again, I'm going to think through it. We've already established that the limit as x approaches infinity of 1 over x is 0, and the limit as x approaches negative infinity of 1 over x is 0. And remember, the properties of limits allow us to evaluate the limit of each term separately and then add them together. So really, to evaluate the limit of this function, for both of these, x approaches infinity and x approaches negative infinity, really would just boil down to adding 2 plus 0, which is just 2. So both limits would be 2, which means that there is a horizontal asymptote at y equals 2. So y, you have to forgive my handwriting here. I'm drawing with the finger pad on the laptop. So that is our horizontal asymptote, because that is the finite value that the limit as x approaches positive or negative infinity approaches. Now, some limits seem a lot more complex when you first look at them, like this one here, x divided by the square root of x squared plus 1. If I look at it graphically, I can get an idea of how it's behaving infinitely to the left and right, negative and positive infinity. So if I look at the graph, I can see that it's kind of flattening out here to the right. That'd be as x approaches positive infinity at y equals 1. And out to the left at y equals negative 1. And so my horizontal asymptotes will be y equals 1 and y equals negative 1. But instead of having to graph it, there are actual rules that you should know from learning horizontal asymptotes. You can look at the degrees of the denominator and the numerator. So if the degree on top is bigger than the degree on the bottom, if you think about that, the top would just get infinitely bigger and bigger and bigger than the bottom, so you're getting a bigger and bigger number, so that's just infinity. And then if the degree on the bottom is bigger, that's like the 1 over x example. If your bottom is just getting bigger and bigger and bigger, then your fraction is getting closer to 0. And the degrees being equal, it's a little less clear, but basically it's the ratio of the leading coefficients. So there's some vocabulary there. Ratio is just a fraction. And then the leading coefficients are the coefficients of the terms with the degree. So it's like if you had 2x squared plus 3x over 4x squared minus 2, then you would take the leading coefficients, 2 over 4. Which would be 1/2. That would be your limit. So looking back at the example I just showed you, you can think through this without having to graph it. And anytime you have a square root of x squared, you combine those two together to get the degree. So square root is the same thing as raising to the 1/2. So if I raise x squared to the 1/2, 2 times 1/2 is 1, so the degree on the bottom would be 1. So the degree is the same on top and bottom, which would make the horizontal asymptote equal to the ratio of the leading coefficients. And so the coefficient on top is 1, coefficient on the bottom is 1, when I'm approaching positive infinity, because positive infinity plugged in for x would be positive. A square root of x squared is always positive. So that would be negative 1. If I have negative infinity and I plug it in for x, that gives me a negative on the top. The bottom will always be positive because it's square root of x squared. So negative over positive is always negative. So that's how you get the negative 1 as the horizontal asymptote. And I will elaborate on this particular example a little more in class, but I just want to introduce you to those rules so you'll have them and be ready to hit the ground running tomorrow.